Welcome back to Linear Algebra. I'm Dr. Jeff Groh. Today we're going to talk about matrix inverses. For real numbers, when you multiply a number by its multiplicative inverse, you get 1. What is 1/2? 1/2 is the multiplicative inverse of 2. When you multiply 2 times its multiplicative inverse, you get 1. How do you do this with respect to a matrix? The first question that needs to be resolved is, what do we mean by 1? Well, that's easy. We already know about the identity matrix. Either I or IN. We use a subscript if we're indicating that it's the n by n identity matrix, and if the size of the matrix is obvious, then we don't need to necessarily to specify the size. As we've seen, if we multiply an identity matrix, which has 1s on the diagonal and 0s everywhere else, by another matrix, we get the other matrix. So I times some matrix is the other matrix. Same goes on the other side, if it has the appropriate order. As you can see, if you have a 2 by 3 matrix, you need to use the 2 by 2 identity on the left and the 3 by 3 identity on the right. You might have a different left versus right identity for a given matrix. Similarly, you might have a different left versus right inverse for a given matrix. Let A be m by n. We say that an n by m matrix B is a left inverse of A if B times A, which is defined because the m's will match, it will yield an n by n matrix. B is a left identity if you get the n by n identity after multiplying. If B is n by m, it is a right inverse if A times B is equal to the m by m identity. Not every matrix has both a left and a right inverse. To give you a simple example, suppose that A is the 1 by 2 matrix, 1, 2. Does it have a left inverse? The left inverse would have to be 2 by 1. That means it would have to be a matrix of the form B equals A, B, so that when you multiply, you get the 2 by 2 identity. As you can see, you'll get A, 2A, B, 2B. This equaling this would imply that A is 1, but also A is 0. That's a contradiction, which means this matrix does not have a left inverse. Does it have a right inverse? The right inverse would be 2 by 1 and would satisfy A times B is the 1 by 1 identity. The 1 by 1 identity is just 1. B would have to have entries A, B. Does such a thing exist? It would have to have the form A plus 2B. A plus 2B equals 1. Well, it seems that there are many such solutions. All we need to do is satisfy the equation 1 equals A plus 2B. There are infinitely many solutions to this. We can choose, for instance, 1 and then 0. This would be a right inverse. So would 0, 1/2. Another obvious solution to this equation. And any number of other answers as well. Choose A and let B be determined by the equation, or vice versa. You can see that we'll have A equals 1 minus 2B. So anytime you have 1 minus 2B, B, for any real number B, this will be a right inverse to this non-square matrix. So thinking about this particular example, it had no left inverse at all, but it has infinitely many right inverses. In fact, we'll make the following definition. Let A be an n by n matrix. We say that B is an inverse of A if the following two conditions hold. B times A is the identity, and A times B is also the identity. So for square matrices, we're going to require, in order to classify some matrix as an inverse, it has to be both a left inverse and a right inverse. Also note that we've said an inverse. We're not assuming that a matrix that is square has only one inverse, if it has one at all. It might have many inverses. Actually, we will prove that if a matrix has an inverse, then it has only one. But that will require proof. Let's look at an example. Suppose my matrix A is 3, 2, 1, 1. Let's see if we can find an inverse to this matrix. A priori, we have no idea what this matrix is. So let's just fill in the blanks with variables, A, B, C, D. We require that the 2 by 2 identity, 1, 0, 0, 1, is equal to the product A times B. That's going to be 3, 2, 1, 1 times A, B, C, D. When we multiply, we'll get 3A plus 2C, 3B plus 2D, and then A plus C, and followed by B plus D. This gives us a system of 4 equations in 4 unknowns. In particular, 3A plus 2C must equal 1. Also, A plus C must equal 0. 3B plus 2D is 0, and B plus D is 1. You can see that if we take these first 2 equations, we can solve those for A and C. In particular, if we multiply the second equation by 2 and subtract, we'll get A equals 1. If A is equal to 1, then C must be, if A is equal to 1, then C must be minus 1. 1 minus 1 is 0, 3 minus 2 is 1. We can do a similar method for solving the second set equations. We'll multiply the second equation through by 2 and then subtract. We'll get 3b minus 2b is b, and 0 minus 2 is minus 2. D is then going to be 3. If b is minus 2 and d is 3, we get 0 in the first equation. Negative 2 plus 3 is 1. We see that the matrix B must in fact be equal to A is 1, B is minus 2, C is minus 1, and then D is 3. Let's check this result. This had better be a right inverse. When we multiply, we'll have 3 minus 2 is 1. Negative 6 and positive 6 is 0. 1 minus 1 is 0. Negative 2 and 3 is 1. And so it checks as a right inverse. What you might not expect is that it is also a left inverse. 3 minus 2 is 1. 2 minus 2 is 0. Negative 3 plus 3 is 0. Negative 2 plus 3 is 1. So in this case, AB is the identity, but BA is also the identity. So this satisfies the left and right inverse definition to be an inverse to the matrix 3, 2, 1, 1. Was there any room in the solution process for finding a different inverse? Is there more than one? I didn't see any way we had more than one solution to that system. We found a unique solution. Is that always going to be the case? When we're talking about a square matrix that has an inverse, does it always have only one inverse? The next theorem asserts that if a matrix has an inverse, it has only one. Let's suppose that this matrix is square. This is a classic uniqueness proof. I want you to learn about uniqueness proofs. They go something like this. If you want to prove there's only one of something, assume there are two, and then prove that in fact they must be equal. Let B1 and B2 be inverses of this square matrix A. We have to ask ourselves, what does it mean to be an inverse? There are those two properties. You're an inverse if you're both a left inverse and a right inverse. We have the following two facts. B1 times A must be the 2 by 2 identity, but that must also be equal to B2 times A, since both B1 and B2 are left inverses. Let's multiply both sides of this equation by B2 on the right. You have to be careful about what side you multiply things on because matrix multiplication is not commutative. We'll have B1A times B2 equals B2A times B2. Now, we can use the associative property to reassociate these products. Now, we assumed that B2 was an inverse. That means it's both a left inverse and a right inverse. So A times B2 must in fact be the identity matrix. And if you multiply the identity matrix on the left or the right times some square matrix, you just get the matrix itself. We deduce then that B1 and B2 are in fact equal. If you have two inverses, they have to be the same. That's the end of the uniqueness proof. So I want you to think about how this proof went. It's characteristic of uniqueness proofs. If you want to prove there's only one of something, assume there are two, and then prove that they must in fact be equal. This uniqueness theorem allows us to introduce some notation. If A has an inverse, then we know it has only one. Denote this unique inverse by A with a superscript of -1. This was not appropriate to do until now, because until we proved the last theorem, for all we knew, there were infinitely many inverses. In fact, as we've seen, for matrices that are not square, you might have an infinite number of right inverses or left inverses. Now that we know that for a square matrix, one that is n by n, if it does have an inverse, that inverse is unique. We will denote it by A with a superscript of -1. There are, of course, square matrices that do not have an inverse at all. Consider the matrix 1, 1, 1, 1. Let's see if we can find an inverse. Suppose B is A, B, C, D, and we want to find B so that B times A is the 2 by 2 identity. That's 1, 0, 0, 1. When we multiply, we'll have A plus B, and then A plus B, followed by C plus D, and then finally C plus D. As you can see, A plus B must be 0. As you can see, A plus B must be 1. But we must also have A plus B equals 0. This leads to the contradictory assertion that 0 equals 1, which means this does not have an inverse at all. For real numbers, the multiplicative inverse of 0 does not exist. Here we had a matrix A, 1, 1, 1, 1, that had no entries equal to 0. This is definitely not equal to the 0 matrix, and yet it still did not have an inverse. This opens a number of questions. Under what conditions does a matrix have an inverse? Is there an easy way to tell whether or not a matrix has an inverse? If a matrix does have an inverse, how do you calculate it efficiently and easily? We're going to introduce some terminology to facilitate our discussion. If a square matrix A, we'll assume that it is n by n, does not have an inverse, then it is called singular, or sometimes non-invertible. Otherwise, it is called non-singular, invertible. So if the matrix does not have an inverse, we call it singular. If it does have an inverse, it is non-singular. We will find a special formula for the inverse if A is 2 by 2. This should be pretty easy. Suppose A is the matrix A, B, C, D. The question that we have is, what is A inverse? Well, let's suppose that A inverse, which we'll assume exists, has the form x, y, z, w. Let's figure out what x, y, z, and w must be in order to have an inverse. This process is going to yield a formula that I require that you memorize. We want the identity matrix to be A times A inverse. So we want 1, 0, 0, 1 to be equal to A, B, C, D times the unknowns x, y, z, w. In other words, we require that AX plus BZ equals 1. Also, AY plus BW is equal to 0. And then CX plus DZ must equal 0, followed by CY plus DW equals 1. This gives us a system of 4 equations in 4 unknowns. We have the equations AX plus BZ equals 1. AY plus BW equals 0. CX plus DZ equals 0. And CY plus DW equals 1. Let's pair these off in the following way. We'll take these 2 equations which involve the unknowns x and z, and we'll solve those for x and z. The other 2 equations only involve y and w. We can solve those for y and w. Let's start with the first 2 equations. AX plus BZ equals 1, and CX plus DZ equals 0. As you can see, I've left a little gap in various spots. That's because we're going to multiply the first equation on both sides by C, and the second equation we're going to multiply on both sides by A. This gives us a new system. We obtain ACX plus BCZ equals C, and also ACX plus ADZ equals 0. Multiply the top equation through by a negative and add. When we do, the x's drop. We will have AD minus BC times Z equals minus C. In other words, Z will be minus C divided by AD minus BC. How about x then? We can back substitute to find x. You will find that x is d divided by AD minus BC. Similarly, on the other pair of equations, we can solve. You will find that y is minus b over AD minus b. C and w is a divided by AD minus BC. Let's check this. I'm claiming that if the matrix A is ABCD and A inverse exists, then A inverse is D over AD minus BC minus B over AD minus BC minus C over AD minus BC, and then A. over AD minus BC. We can simplify the computation if we simply factor out 1 over AD minus BC as a scalar times the matrix D minus B minus C A. It turns out AD minus BC, AD minus BC, kind of a criss-cross product and a subtraction, is called the determinant of this matrix. So we'll get 1 over the determinant times the matrix that you get by switching A and D back and forth. D goes up here and A goes down here, and then negating the elements off of the main diagonal. This should give you the inverse, but does it? We have to check. Here's our check. We'll multiply our proposed inverse by the matrix A, B, C, D, and hope to get the identity matrix. As you can see, you'll get AD minus BC, and then BD minus BD, minus AC plus AC, and then minus BC plus AD. Multiplying through by the scalar, we get 1001, or the 2 by 2 identity. We have in fact now proved a very important method for finding the inverse of any invertible 2 by 2 matrix. We have the following theorem. Let the matrix A be A, B, C, D. If AD minus BC is not 0, then the inverse must exist, because we know how to calculate it in this case. If AD minus BC is 0, you get 1 over 0 out front of our proposed inverse formula, and that leaves an inverse undefined. So then A inverse exists provided the determinant AD minus BC is non-zero, and we can calculate exactly what that inverse is. It's 1 over the determinant, 1 over AD minus BC, times the matrix that you get by switching A and D and then negating B and C, the elements off of the main diagonal. This is a formula that I require that you memorize. For example, suppose A is the matrix 3, 3, 1, 2. A inverse should be 1 over the determinant, that's going to be 6 minus 3, switch the diagonal elements and negate the off-diagonal elements. This gives us the matrix 2/3, negative 1, negative 1/3, 1. We can check this directly by multiplying by the original matrix. Let's calculate A times A inverse. That's going to be 3, 3, 1, 2 times 2/3 minus 1 minus 1/3, 1. We'll get 3 times 2/3 is 2, minus 1 is 1. Negative 3 plus 3 is 0. 2/3 minus 2/3 is 0. Minus 1 plus 2 is 1. You can check separately that this also represents a left inverse. We've proved that it is in fact a right inverse. In fact, we will show that if a square matrix is invertible, then the right inverse will equal the left inverse. Let A, which is n by n, and B, which is also n by n, be invertible. Then A times B is invertible. And here's the important formula. If you calculate the inverse of a product, the inverse will be B inverse times A inverse. Take special note of the order in which the factors are written. The order of the factors will be reversed when you distribute the exponent to the two factors. To prove the invertibility of the product AB, all we have to do is exhibit an inverse. Here's what we'll do. We'll take AB and multiply it by B inverse A inverse. If we can prove that this is the identity matrix, then B inverse A inverse will be a right inverse to AB. We'll have to check the left inverse side as well. By the associative law, we can rewrite this as B times B inverse A inverse, which is A times the identity times A inverse. That's A times A inverse, and that's the identity. That proves that B inverse A inverse is a right inverse to the product AB. We have to check it the other way around. B inverse A inverse on the left, which follows the same path. Use the associative law. Use the fact that A inverse A is the identity. The identity behaves like the identity should, and then B is an inverse of B, and then B inverse is the inverse of B, so you get the identity. We deduce then, therefore, that AB's inverse is in fact B inverse A inverse, and that is the end of the proof. Now, if A is invertible or non-singular, and B is a right inverse, then B is also a left inverse. Proof goes like this. If B is a right inverse, then A times B is the identity. Since A is invertible, we can multiply both sides on the left by A inverse. A inverse times A is the identity, so you get B equals A inverse. Remember, an inverse is both a left and a right inverse. That implies B is also a left inverse, and hence is equal to the unique inverse. This theorem means that if we find a right inverse to a matrix, then it is the unique inverse, and we don't have to check that it is also a left inverse. We have a slick formula for finding the inverse of any 2 by 2 matrix. But what if the matrix is 3 by 3 or 4 by 4? We have to solve A times A inverse equals the identity matrix. Let's think about it like this. Let's suppose A inverse is expressible as maybe a column vector and then another column vector, and it will have n different columns. If we multiply A times A inverse, what we'll get is A times column 1, A times column 2, down to A times column n. The identity matrix will be 1, 0, and a bunch of zeros, followed by 0, 1, and then a bunch of zeros, and so forth until we get to 0, 0, and then terminating at a 1. In other words, we have to solve the following system of equations. To facilitate this discussion, I'm going to introduce some notation. Let's suppose that E1 is the vector 1, 0, and then a bunch of zeros. E2 is the vector 0, 1, 0, and then zeros. So it has a 1 in the second row and zeros everywhere else. What we need to do is we need to solve AC1 equals E1. We can put a little arrow over the top to indicate that we're dealing with a vector. Also, AC2 equals E2. Down to ACN equals EN. That's a lot of systems of equations that we have to solve. Think about how many row operations we'll need to perform. There is a lot of redundancy in those row operations. If we're always trying to find the reduced row echelon form for each and every single one of these systems, and if they all have exactly the same coefficient matrix A, you will perform exactly the same sequence of elementary row operations in order to solve the systems. You might be better off if you did the following. If you had the matrix A times this unknown, let's call it big matrix C, equals the identity matrix. C is kind of the unknown here, but it's an n by n matrix. You can solve that by solving the following augmented array. Instead of putting a vector down on the right-hand sides after the vertical slash, put the entire identity matrix down. Perform elementary row operations until you get to the reduced row echelon form, at which point, on the left, you should have the identity matrix, and whatever appears on the right will be the entries of the matrix C that gives you the inverse. This method should work no matter how big the matrix is. To see how it works with respect to a 2 by 2, where we already have a different formula, let's try it out on, let's say, 3, 2, 1, 1. We want to find the inverse. So what we'll do is put this next to 1, 0, 0, 1. And we'll perform elementary row operations. For instance, we can switch row 1 and row 2, and that'll give us a leading 1. And then take -3 times row 1 and add it to row 2, yielding a new row 2. -3 times 1 plus 3 is 0. -3 times 1 plus 2 is -1. We'll have 1 and then -3. We'll multiply through by a -1 on the second row. Negative row 2 yields a new row 2. And then we need to get a 0 above the leading one in the second row. So negative row 2 plus row 1 yields a new row 1. That leaves the second row alone. And we'll get 1, 0. -1 times -1 plus 0 is +1. -3 plus 1 is -2. We deduce that our inverse matrix is, in fact, 1, -2, -1, 3. Let's check this by the other method. Let's try this out. The other method was take 1 over the determinant, reverse the diagonal elements, and negate the off diagonals. We get 3 minus 2 is 1. And so we just end up with 1 minus 2 minus 1, 3, which is the same. You can see then that this method does work. It's not as fast as our quick, slick formula in the 2 by 2 case, but the 2 by 2 case only works if the matrix involved is 2 by 2. What if it's 3 by 3? Then you have to use this other method. Let's use this method for calculating the inverse of this 3 by 3 matrix. Yes, I know you can just enter the matrix into your calculator and have it calculate the inverse in a few seconds, but you need to know what the calculator is doing behind the scenes. Here's what's happening. We'll take the matrix A and abut it next to the identity matrix. And then we'll perform a sequence of elementary row operations until we get the identity matrix on the left. Whatever appears on the right will be the inverse. So let's first do two elementary row operations. -2 times row 1 plus row 2 yields a new row 2. That'll put a 0 under this leading 1. And -3 times row 1 plus row 3 yields a new row 3. That'll give us zeros underneath this leading one in the first row. -2 times this plus this is 0. -2 times -1 is +2, plus 1 is 3. We're not changing the first row, and that's the only row that we're not changing. -2 times 3 is -6, plus 0 is -6. -2 times 1 plus 0 is -2. -3 times 1 plus 3 is 0. -3 times -1 is +3, plus 2 is 5. -3 times 3 is -9, plus 1 is -8. We'll have -3, 0, and then 1. Now we can get a 1 into the leading position in the second row by multiplying through by 1/3. 1/3 row 2 yields a new row 2. On the right side we'll get -2/3, 1/3, 0. Now, we have a leading 1 on the second row. If we take row 2 plus row 1 yields a new row 1, and -5 times row 2 plus row 3 yields a new row 3, that leaves the second row alone. One plus -1 is 0. -2 plus 3 is 1. -2/3 plus 1 is 1/3. 1/3 plus 1/3 is 1/3. We get a 0 in the last position. -5 times 1 plus 5 is 0. -5 times -2 is +10, plus -8 is +2. -5 times -2/3 is +10/3. 10/3 and -9/3 is 1/3. -5/3 plus 0 is -5/3, and then 1. An easy calculation to do right away is to take row 3 and add it to row 2. That'll give us 0, 1, 0. 1/3 and -2/3 is -1/3. -5/3 plus 1/3 is -4/3. And then we get a 1 in this last position. The first row remains unchanged. The next step is to multiply the last row through by 1/2. We can then leverage that to get a 0 in the first row above the leading one in the third row. We'll do 1/2 row 3 yields a new row 3. That leaves the first two rows unchanged. We'll have 1/6, -5/6, and 1/2. We now need to take negative row 3 plus row 1 yields a new row 1. That will be the final step leading to an identity matrix on the left side of the vertical slash in our augmented array. The last two rows do not change. -1/3, -4/3, 1, 1/6, -5/6, 1/2. -1/6 plus 2/6 is positive 1/6. We're multiplying through by a negative. We'll have 5/6 plus 5/6 plus 2/6 is 7/6. -1/2 plus 0 is -1/2. We should now have our inverse. Our inverse must be 1/6, 7/6, -1/2, -1/3, -4/3, 1, 1/6, -5/6, and then positive 1/2. I have to be honest with you. I had to do this computation twice because I made an arithmetic error. The more you do, the more mistakes you're going to make. It's just going to happen. That's the price you pay for being human. However, I wanted you to see in detail every single step. I know this is the correct answer because, first of all, we just calculated it. Also, I checked it on my calculator, and I've done this earlier and written the answer on the note card that I have. So I triple checked it, but you need to know every single step along the way. Also, I did tell you on the first lecture for this course that there would be a mind-numbingly boring amount of simple arithmetic. I think this example proves it. Yes, we could have entered the matrix, hit the inverse button on our calculator, and come up with this very quickly, but you wouldn't understand the theory about how you get inverses. I want to show you how to calculate the inverse on your calculator. So first we have to enter the matrix. Second matrix. Let's go to edit, and we're going to enter a 3x3 matrix here. I already have the entries all in there, but I'll just show you how you enter them anyway. So second quit to get out of that then. Second matrix. We're just going to click on 1 and then hit the inverse button right there. If you hit enter now, you get the inverse, but it's all decimals. I'd rather have fractions, so we'll hit math frac, and then there it is. That's the matrix that we found. I want you to know what to look for if the inverse does not exist. So we're going to look at this example where the inverse doesn't exist. How do you know? Here's what we'll do. We'll set it up as though we are solving for the inverse, and we will perform elementary row operations. Let's do the following. -2 times row 1 plus row 2 yields a new row 2. And -3 times row 1 plus row 3 yields a new row 3. The only row that doesn't change is the first row. -2 times this plus this. 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 -3 times this plus this. -3 times this plus this. -3 times this plus this. negative 3 times this plus this, negative 3 times this plus this, and there. Before getting too carried away, let's try negative row 2 plus row 3 yields a new row 3. Negative 1 times this plus this, 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 and there. Now we see something peculiar. We have zeros all the way across this last row. If you get zeros all the way across, there's no way you can use any sequence of elementary row operations to get the identity matrix. It's not going to be row equivalent to the identity matrix on the left, which means the inverse doesn't exist. DNE does not exist. You can see that because you'll have an inconsistent equation here, a contradiction. As we've mentioned already, matrices don't have a cancellation law except if you have an invertible matrix involved. Let A be non-singular. I'm mixing up the terminology so you'll get used to it. Non-singular just means that the inverse exists. It's invertible. Then AX equals AY implies X equals Y. So if you have A on the left of matrices X and Y, you can deduce that X equals Y. You can see this because you just multiply on the left by A inverse. And you can take A inverse times A to get the identity. The identity times X is X. Same thing on the right. Also, if you have XA equals YA, you can multiply by A inverse on the right and deduce that X equals Y. However, if A is on the right, on the left side of the equation, and on the left, on the right-hand side of the equation, if you got it mixed up, you can't cancel the matrix A off. The proof is just what we described. AX equals AY implies you can multiply on the left by A inverse. By the associative law, you can reassociate. That's a Y on this side. You get the identity times X equals the identity times Y. In other words, X equals Y. The other case is similar. We are going to apply this inverse theory to solve systems of equations. If A is an n by n matrix, and if it is invertible, and also if B is any element of Rn, so it's a matrix having real entries, a vector having real entries, then AX equals B has a unique solution. There's only one solution, and it does exist. And the solution X is A inverse B. Let's prove this. Consider AX equals B. We've assumed that A is invertible, so we'll multiply both sides of this equation on the left by A inverse. By the associative property, we can associate A on the left with A inverse, but that gives you the identity. But the identity times a matrix is the other matrix, so the solution is the one and only solution, A inverse times B. This gives us a new method for solving systems of equations. So far we've talked about Gaussian elimination with backward substitution and also Gauss-Jordan elimination. Now we have the inverse matrix method. For solving systems of equations. We simply take the right-hand side, multiply it on the left by the inverse matrix. Let's do this. Suppose we have 3x plus 2y equals 5 and x plus y equals, let's say, 4. We can rewrite this as a matrix system. 3, 2, 1, 1 times xy equals 5, 4. This is now in the form ax equals b. The solution x, which will be the coordinates xy, will be A inverse times b. A inverse is 1 over the determinant. Switch the diagonal elements and negate the off-diagonal elements. Notice that 3 minus 2 is 1. When we multiply now, we'll have 5 minus 8 is negative 3. Negative 5 plus 12 is 7. We get x equals negative 3, y equals 7. Let's see if that works. Negative 3 plus 7 is 4. It satisfies the second equation, makes a true statement. 3 times negative 3 is negative 9, plus 14. 14 minus 9 is 5. So this point satisfies both equations. It is the common point of intersection of those two straight lines. We're going to study systems of equations in a bit more depth. Given a linear system in matrix form, ax equals b, the corresponding homogeneous system is ax equals 0. Note that if A is m by n and then x is n by 1, then B must be m by 1. If these match, the product ends up being this order, m by 1. Also, if ax equals 0, where here we're dealing with the 0 in Rm, then x equals 0 in Rn is a solution. The 0 vector in the domain will always be a solution to a homogeneous system. We call this the trivial solution. There may be other solutions, but this one certainly will be trivially so. The trivial solution to x equals 0 is x equals 0. Keeping in mind that the 0 on this side is a little different from the 0 on the other side. This was in m-dimensional space, this one in n-dimensional space. Nonetheless, the 0 vector in the domain will always solve a homogeneous linear system. I want to state a theorem. If, let's say, x hat solves ax equals b, and x tilde solves the corresponding homogeneous system AX equals 0, then for any scalar c, x, let's call this x bar, which is equal to x hat plus c times x tilde, this will also be a solution to AX equals B. In other words, if you have any given solution to a linear system plus any other solution to the corresponding homogeneous equation, then you can find an infinite number of other solutions to the original system by taking the non-homogeneous solution and adding any scalar multiple of that homogeneous solution. Let's prove this. We'll begin by supposing that AX hat is B and AX tilde is the zero vector. We'll look at A times x hat plus c times x tilde. By the distributive property, we get AX hat plus c times AX tilde. Remember that scalars commute with everything, so the scalar c can be brought out front. A times x hat is b, and we'll get c times the zero vector, so we just end up with b. That's the end of the proof. So anything of the form non-homogeneous solution plus an arbitrary constant times a homogeneous solution will be a non-homogeneous solution. Let's look at an example. Suppose we have 1, 2, -2, -4, 3, 6 as our matrix A. Let's look at the system where x, in this case, is the vector xy, the vector of unknowns, and b will be the vector, let's say, 2, -4, and 6. Can we solve this system AX equals B? Well, this is not a square matrix, so A inverse doesn't exist. We can't use the inverse matrix method to solve this, but we can use Gaussian elimination. Let's see, we'll do 2 times row 1 plus row 2 yields a new row 2, and -3 times row 1 plus row 3 yields a new row 3. We'll have 0, 0, 0, and then 0, 0, 0. We are now in reduced row echelon form. What is the solution? Well, there are infinitely many solutions. What's left represents the equation x plus 2y equals 2. There are infinitely many solutions. X is 2 minus 2y. Whatever the solution is, x is going to be 2 minus 2y, where y is whatever it is. We can think of our solution xy as being of the form 2, 0 plus y, where y is any parameter at all, times -2, 1. So if y is 0, then x equals 2, y equals 0 works. That should certainly be one solution. I want to think about this other part, this part -2, 1. You'll remember that the original matrix was 1, 2, -2, -4, 3, 6. I'm going to multiply that by -2, 1 and see what I get. I'll have -2 and 2 makes 0. +4 and -4 makes 0. -6 and 6 makes 0. That means This is a homogeneous solution. This solution, xy, is in exactly the form of the last theorem. It's a non-homogeneous solution plus a scalar times a homogeneous solution. Any scalar times that plus this yields yet another solution. We have infinitely many solutions to this system. This will, in this particular instance, give us all of them. But note the form. It's a non-homogeneous solution plus a scalar times a homogeneous solution. You can see a theorem in the offing. If you want to solve a system of equations, yes, you do need to find a solution to a non-homogeneous equation, but you also need to find the entire solution space to the corresponding homogeneous solution. This is going to be a part of your future.